Google's new quantum chip, Willow, has achieved remarkable computational feats. It notably completed tasks in minutes that would take classical supercomputers an estimated 10 septillion years. This performance has reignited discussions about the many-worlds interpretation of quantum mechanics. This theory suggests that all possible outcomes of quantum measurements are realized in separate, branching universes. Hartmut Neven suggested that Willow's capabilities lend credence to the notion that quantum computations occur across many parallel universes. This aligns with the many-worlds interpretation theory. This perspective echoes physicist David Deutsch's hypothesis. He theorized that quantum computing's power stems from simultaneous computations in multiple universes. While Willow's achievements represent a significant milestone in quantum computing, they do not conclusively demonstrate the existence of alternate universes. If it did offer proof, it would have profound implications. We'll examine what such a discovery might mean. If quantum computing proved the existence of alternate universes, it could mean that every possible outcome of a quantum event does indeed create a separate, parallel universe. For example, whenever you make a decision, in one universe you chose a coffee this morning, and in another you chose tea. This would fundamentally shift how we understand reality, suggesting that we live in a multiverse rather than a single, linear universe. If Google's quantum chip, Willow, truly interacted with multiple universes, as suggested by some interpretations of quantum mechanics, it would represent an extraordinary leap in our understanding of reality. In the many-worlds interpretation, quantum events branch into parallel universes, each corresponding to a possible outcome. If Willow were interacting with these universes, it might mean it could harness computations spread across multiple branches of reality. Quantum systems already exist in superpositions of states until measured. If Willow explicitly accesses other universes, it could mean superpositions are tied directly to alternate realities. Willow might perform calculations not just through superposition and entanglement, but by leveraging resources from alternate realities. This could make it exponentially more powerful than traditional quantum computers. Researchers might develop algorithms that explicitly exploit interactions between universes, solving problems otherwise thought intractable. If Willow accesses alternate universes, it raises the question of whether information could flow between them. Could we receive data from or send messages to parallel realities? This might allow glimpses into how events unfolded differently in other universes, potentially shedding light on what-if scenarios. Interactions could lead to ethical dilemmas, e.g., how would actions in one universe affect another? Could we influence the course of events across realities? Confirming such interactions would demand a revision of current quantum theories and a deeper understanding of multiverse physics. Designing experiments to test and verify these interactions would be extraordinarily complex. Would the interactions leave measurable signatures in our universe? Even if the interaction exists, accessing or controlling it might be far beyond our technological capabilities. If interaction with alternate universes is possible, it could open pathways to exploring alternate histories. It could also lead to practical problem-solving by accessing solutions from realities where different choices were made. It could also lead to existential questions, such as examining whether free will exists if all possibilities play out in parallel. The concept is highly speculative, and most physicists would emphasize caution before jumping to conclusions. However, even the suggestion of such interaction would profoundly reshape both science and philosophy. It's important to note that what follows is purely theoretical. However, if the multiverse theory proves correct, let's explore what might become possible. Dr. Sarah Chen, a brilliant quantum physicist, was about to change our understanding of reality itself. Her breakthrough wasn't just another quantum computer. It was a bridge between universes. The quantum multiverse processor could reach across dimensional boundaries, accessing billions of parallel realities simultaneously. Unlike traditional quantum computers that merely simulated multiple states, this chip actually tapped into alternate universes. Investment firms were the first to harness this power, testing millions of trading strategies across parallel realities. Medical researchers followed, exploring countless drug combinations in parallel universes. But the true revolution came when historians began exploring what they called reality branches. They witnessed worlds where the Library of Alexandria never burned, where the Industrial Revolution began in China. Each small change created ripples across the multiverse, spawning entirely new realities. This raised profound questions about free will and determinism. Were we truly free to shape our destiny, or were we exploring pre-written variations of reality? The answer, like quantum mechanics itself, existed in a superposition of possibilities. Dr. Chen's invention had given us a window into the true nature of reality. But like all windows, it showed us as much about ourselves as what lay beyond. We stood at the intersection of infinite possibilities, forever changed by the knowledge that every choice we make echoes across countless universes. The line between possible and impossible had not just blurred, it had vanished entirely. Although quantum computing is in its early stages, current quantum chips are currently being tested on optimization problems, logistics, scheduling, and supply chain optimization, quantum chemistry, simulating molecules to aid in drug discovery or material science, machine learning, quantum-enhanced algorithms for faster data processing, cryptography, developing quantum-safe encryption and breaking classical encryption systems, a future risk. The early and major players in quantum chips, Google, pioneer of quantum supremacy in chips like Sycamore and Willow. IBM focused on scalable quantum systems, offering quantum cloud platforms. Intel, developing spin qubits and advanced packaging for quantum chips. Rigetti, creating cloud-accessible quantum computers using superconducting qubits. IonQ and Honeywell, leaders in trapped ion technologies. D-Wave, specialized in quantum annealing for optimization problems. Future advancements in quantum chips will focus on error-resilient architectures, logical qubits that are immune to errors, higher qubit counts, chips with thousands of qubits for practical applications, room temperature systems, efforts to eliminate the need for cryogenics, commercialization, more accessible and practical quantum computing as the hardware matures. While we're far from achieving a universal quantum computer, the field is advancing at an accelerating pace, with quantum chips at the heart of this technological revolution.